So thanks a lot, Jairo, for your great introduction. I don't agree that it's just my work. It's our work we did together with Jairo, and as he said, with Dr. Jakub Železný and Professor Tomáš Jungwirth in Prague. And also, let me thank to the organizers, because I will be very happy to share with you our recent work about topological antiferromagnetic spintronics, because there is a Spintronics and the conference is mostly about topology and Dirac systems. I will also have a brief introduction about Neél Spinorbit Torques, and I will take you on the retour how to go from these Neél Spinorbit Torques to Dirac fermions in antiferromagnets. So the talk is divided basically into two parts. In the first part, there will be this introduction. We will start with very simple pictures with ferromagnetic systems, which are much easier to understand. And after the introduction, I will come to maybe more exciting topics for the audience, and these are antiferromagnet, which are topological. And there I will talk about our recent papers on this topic. So this is an example, actually, of a band structure in topological antiferromagnet. So let me start with prominent Spintronics phenomena. So basically, in last 2 decades, we have seen that in Spintronics, people started to be interested more in effects which are based on relativistic quantum mechanics instead of exchange coupling, like in giant magnetoresistance. And the most relevant for what I will be talking about are actually spin Hall effect and inverse spin galvanic effect. And these are effects which we can use nowadays to generate spin via electric current in real devices, which can be eventually interesting also for industry, because there is a huge hope that these extremely large spin orbit fields, which are generated here in these heavy metals, can be used effectively in magnetic random access memories. So in spin Hall effect, you basically, due to large spin orbit coupling, generate the spin current, and at the edges of your sample, you have a spin non-equilibrium spin polarization. In the inverse spin galvanic effect, you have a local non-equilibrium spin polarization, which comes from the fact that you have a local or global symmetry breaking in your magnet. Now, how to understand it a little bit more physical. So we can take a Kubo formula for quantum transport, where we have distribution functions, and we have here basically the operators where we push. So this is the electric field, and here we have our response. So we want to get the expectation value of the spin. We want to get this non-equilibrium spin polarizations. And the first mechanism how to get it is that basically you can change these things. These things can change because of the current. So this is without any current. This is a spin texture in the K-space in such a system. And once you run a current, because it's non-central symmetric, you will generate at globally in the sample more, let's say, spin up than spin down. There is missing second figure, which would be for the spin down. But because of the symmetry breaking, one spin component dominates. And this leads to this spin accumulation due to the non-equilibrium distribution function change. In the second scenario, you have actually constant these guys, but you can have changes in the quantum states. So in this case, let me start with such a spin texture where you have also strong exchange. So it could be some ferromagnet, for instance. And you see that the spins already in equilibrium orient in one direction along the 100 axis. And once you start to run electric current through your systems, you will generate basically non-equilibrium fields which will tilt your spins, and this is then this intrinsic contribution coming from the changes in the wave functions. Now, we are able to generate these non-equilibrium spin polarizations, and we can do with it very interesting things, and Spintronics focused in a recent decade mainly on spin-orbit torques. So once you generate in this heavy metal layer, once you generate these non-equilibrium spin polarizations, you can basically create a torque on the adjacent ferromagnet. And you have several scenarios which emerge basically in these works. So in the beginning, people thought that in a scenario where you have a spin Hall effect, and then you have something like spin transfer torques, or the usual Slonchevsky type of torque in a Landau-Cauchy-Gilbert equation. You get this type of symmetry, so you have this anti-damping-like torque, and this was such a heterostructure studied by those guys. In the Edelstein scenario, people obtained it originally field-like type of torque, which has this type of symmetry. But after 10 years of research, it turns out that actually these are just two very limiting cases. And because you have these heterostructures, you have several contributions coming from the bulk, eventually bulk effects and the interfacial effects. So you want to potentially disentangle these contributions. So to see really the physical origin of this guy, of this spin orbit torque. And to do that, you need to get rid somehow of this heterostructure, and you need to get just simple magnet which can reverse itself. But before showing that, I want to mention that the broken inversion symmetry is really important. As you can see from the symmetry properties of the torquance tensor, which is defined via this relation, and you can see that the guys which come into these equations, they transfer under the spatial inversion and time reversal symmetry as this. So this means that you need to look not only at Laue point group, but you need to look at the magnetic point group when you look at this spin orbit torquance tensor. And for that, this will be non-zero only when you have the non-centrosymmetricity in your system. So now, in very recent years, like 2, 3, 4 years ago, people started, of course, to use yet another way how to generate spin currents, and this is the quantum spin-hole effect or topological insulators. Well, they used some magnetically doped topological insulator. On the top of it, they put topological insulator, and they try to torque, due to this spin momentum lock Dirac quasiparticles, the adjacent ferromagnetic magnetically doped topological insulator. Well, they got increase in the efficiency by 3 orders of magnitude, but at very low temperatures. So this is not definitely the final answer. And also this mechanism of those guys is already controversial. So while here, it's even more controversial. So, and also the dominating contribution is of the anti-damping-like nature. Then work of Jairo and Tomáš have shown actually that in systems where you have bulky non-centrosymmetricity, so for instance this gallium manganese arsenic system, you see that in the crystal, if you take these two atoms, gallium and arsenic, and here you have in the original zinc blende lattice with the same atoms, you have the center of inversion. When you have two different atoms, you have not anymore, you don't have it. So you generate, when you run a current, you generate non-equilibrium polarization just already in this single layer of gallium manganese arsenic. And then practically what you do is that you look at the DC voltage which is generated by the microwave, and then you can distinguish two contributions. One is symmetric, and this corresponds to anti-damping-like torque. One is antisymmetric, this corresponds to field-like torque. And also you get a different type of symmetries depending on the strain which you induce. This is not surprising. This is like with the usual semiconductors, that you can get either Rashba or Dresselhaus type of symmetry. So in the end, this was a beautiful work where for the first time was shown that you can get intrinsic type of spin orbit torque, which is very analogical to the original proposal of intrinsic spin-hole effect. And you see that at the same time, also in this system, the other contribution from the field-like is similarly important. This is not the case in a sister compound, but in a metallic case, not in a semiconducting case. So in Heusler, half-Heusler nickel manganese antimony, we have shown that you can basically do the same experiment, and what you get is a signal which signals that you have actually dominating the field-like type of torque. And how we get these signals? We get them via anisotropic magnetoresistance, which is defined as the difference between the resistivity corresponding to the state where you are rotating your magnetization with respect to the electric current minus the magnetization with respect to the bare electric current. And these curves, you see, this is calculated ab initio, and this is experimental data. So you see that we have a very nice fit between them. You see that the trend that along this crystallographic direction you have a larger signal is very nicely reproduced. So this is not easy to get. This is a lot of calculations, but this is showing us that we can maybe turn even into more involved systems like antiferromagnets. So why antiferromagnets? So antiferromagnets are interesting for several reasons. You can basically get faster dynamics. You have also larger palette of materials because, for instance, in ferromagnets you had huge problems to get semiconducting ferromagnetism at room temperature. In antiferromagnets you have many natural candidates which persist above room temperature, far above. For instance, some of the systems can reach 500K, 1500K in the Neél temperature. And in recent years, several works have shown that you can do similar type of things as with ferromagnets, so that some effects are equally present, as for instance this anisotropic magnetoresistance in antiferromagnets as in ferromagnets. So here you see that when you rotate the staggered order in the antiferromagnet, the resistivity of your system changes. But more surprisingly, people, Tomáš and Jairo, they discovered that you can have also Neél Spinorbit torques, which actually follow the symmetry of your magnetic sublattice. So when you look now at these two magnetic sublattices with the opposite magnetic moment, you can see that once you run a current through the system, you will generate in this type of symmetry where you have basically connected them due to the center of inversion in the paramagnetic state, but in the magnetic state, the symmetry is broken by the opposite magnetic moment on these sublattices. You can see that actually the non-equilibrium fields are exactly opposite, so they are efficient. This is a dream what you want to do with antiferromagnets, because originally what you would like to do, you want to really take a magnet and put it next to each other spin with the corresponding magnetic moment, which is not possible in reality, but these fields are doing exactly this job for you, as you can see on this animation. So this is not how it works, but this is a picture to imagine how it works. So these abstract non-equilibrium polarizations, what they are doing is that once you run a current through the systems, you can imagine that they create such coils around your atoms, and they have the opposite chirality of the current, and this then torques and switches your Neél order. So this was a beautiful work last year by Pete Wedley and Thomas Jungwirth, who basically tested the system in such a typical 8-star probe current scenario. So they run in one direction current, in another one they measure, and what they see when they pulse the system with larger and larger amplitudes of the density of the current, they see that they can really switch the state which is here. So this is amazing, because this is a dream of Neél already from 1970s, who said that antiferromagnets are extremely interesting for many reasons, but we cannot do anything with them because we cannot manipulate them, because you cannot just put it into magnetic field. You don't have enough magnetic field to manipulate them as you want. But this relativistic physics is doing this job for you. So this is extremely exciting, and it opens many avenues. And we will look at some of them. But first, let me also say that we now understand very well anisotropic magnetoresistance, so the red out type of thing for antiferromagnets. You can see that this is again ab initio calculation of the resistivity, residual resistivity independence of two types of disorder, and this is the AMR values. And when you put their experimental values, you see that you get again very nice results. So to get such accordance is really not easy, and you can do very difficult calculations. And if anybody is interested, I would like to discuss it during the rest of the conference. So now let me go to the second part. So I said this showing that antiferromagnets can do really something active in nanospintronic devices is also giving new ideas. And one of the ideas is that when you have a I'm too far away. When you have a let's say, Dirac quasi-particle system, like topological system. This is one of the main topics of this conference. And then you have things like this relativistic spintronics, where the recent development includes Neél type of spin-orbit torques. You can ask whether we can put these two things together, because they are somehow developing over the recent 10 years independently on each other. And if you start to look for these overlaps, so one of the first things which you will find is that you can really do something in this heterostructure. So you just really force them. You know, you just take the topological system, you take the spintronic system, you force them, and you are looking what is happening. But as I said, there are many troubles. So, for instance, the magnetism in these magnetically doped topological insulators is very fragile, because it's usually interfacial, and it also persists just at low temperatures. And also, you have still the low dimensionality, which is also still one of the main obstacles of topological insulators. Surprisingly, we will see now that antiferromagnets can do for us some interesting things. And I pick up this specific minimal Dirac antiferromagnet, where I want to show the basic physics. And now I will design the symmetry criteria for that guy. So if you look at those, what you need, definitely you need at least two sides in the unit cell. Because regarding Dirac quasi-particles, you will get probably, due to the band folding, some band crossings. And at the same time, you need to get these Neél spin-orbit torques. So you need to get these staggered fields, so also two sides in unit cell. The second step is that you need to get a PT symmetry. Surprisingly, you can reformulate the criteria which I was heuristically talking about for the Neél spin-orbit torques. You can reformulate them in terms of PT symmetry. Because these two sublattices are connected, or these two are connected due to this PT inversion symmetry, time reversal symmetry combined center. So you see that what is inversion symmetry doing with spins? Okay, nothing. And what is doing time reversal symmetry with spin is reverses. So this is definitely the symmetry of this guy. This is also symmetry of this guy. This symmetry is giving us the known Kramer's theorem, as we already heard in the morning. And at the same time, it is giving us this set of conditions which result into non-zero Neél spin-orbit torques. And the third thing is that we want to do something with it, something active in the device. So we impose some additional symmetry, which we can control somehow, and we end up with such a quasi-two-dimensional system. This quasi-two-dimensional system can be understood by crickling such a two-dimensional square lattice. When you take these two antiferromagnetic sublattices and you shift them in the z direction in the opposite direction, then you generate Kane-Meller spin-orbit coupling, and you will generate also these non-equilibrium spin polarizations. The Hamiltonian in real space is looking like that. We could also derive such a model from more general perspective, because we can look at what we want. So we want the Dirac Hamiltonian. This is the easiest 4x4 system. So the general 4x4 Dirac Hamiltonian has such a form, and we can think about antiferromagnet as being composed from the crystal momentum dependent part, where you can tune 3 crystal momenta components, and then you can tune by 2 general angles the Neél vector orientation. So when you impose that you wrap it on some periodic space, you can end up always with some band crossings which you can close and open. And also, this is not only interesting for the applications, but this is also interesting for some more esoteric topics, like algebra of Twistall theory, for instance. Well, we constructed such a model with the hoppings, nearest and next nearest neighbors hoppings. Then we have this double Rajva spin-orbit coupling, which follows the PT symmetry, because you have here this tau z spin matrix, which is swapping the sides, exactly what you want. And then we have here this normal antiferromagnetic Zeeman field. Well, the system has, on top of all these beautiful symmetries, also this non-symmetric. Non-symmetric means that you couple the point group symmetry with some non-trivial spatial translation, and this symmetry is then giving you this allocation of the bands on the submanifolds in the Brillouin zone, which are invariant under this symmetry, as you can see in this K.P Hamiltonian. So this is when you do it around these 2 Dirac points, which you have seen in the previous band structure, and you see that in my basis, which I have chosen, the glide mirror plane operator is given by this expression, which obviously at this line commutes with this Hamiltonian. So we have a protected Dirac points in 2D, and we can generalize the model. We can introduce coupling to adjacent layers. We can stack it, something as, again, Shuchi already have shown in a morning for the topological insulators. And when we do that, we can arrive at the topologically protected nodal line semimetal, where you can tune several interesting properties by, for instance, tuning spin-orbit coupling. And so, for instance, this nodal line corresponds to this situation. Now we came to the point where we want to find real material candidates at which we can look in the experiment. And surprisingly, the copper manganese arsenic, where the spin-orbit torques were first shown, is showing deep in the Fermi sea these topological nodal lines, protected exactly by this symmetry. So it's the same physics as in the model. But this is not enough, right? So we need to go for something at the Fermi energy. We can expect some transport manifestation directly in magnetoresistance, for instance. And well, this orthorhombic variant, which has twice as large the unit cell as the tetragonal one, is giving you exactly what you need. So you see that if you calculate the non-equilibrium string polarizations, they follow the PT symmetry. And then you want to look at these guys, what is happening with them when you run a current through your sample. And that's the most interesting point, because you start, let's say, with your moments along the z direction, for which you have such an assignment of the symmetry to the bands that you have a protected crystalline Dirac semimetal antiferromagnet due to this screw axis, which I just am drawing. And you have also density of states which corresponds exactly to 3D Dirac semimetal. Now you run a current in the y direction. In this direction, you reorient your staggered order, and you end up with insulator. So what you had metal insulator transition, which will have influence on your transport properties, as we will see in the next slide, because here I run a current, generate these non-equilibrium polarizations, and what is doing the longitudinal conductivity, you see that from some finite Dirac value, you end up with the insulating. So you can have large, extremely huge anisotropic magnetoresistance. You remember maybe before that in this nickel manganese antimony, manganese to gold, the values were 1, 2%, maybe 8% is the top. But this can be in principle limitless. So this is a way, of course, in experiment, not because you need to have some reasonably large band gaps, but this can give you really comparable values in principle with the giant magnetoresistance, with extreme magnetoresistance, colossal magnetoresistance. And it's definitely much suited for Spintronics than other type of magnetoresistance. So this brings me basically to the conclusion that we have shown one example, but there are more, of the topological antiferromagnets. So you can merge topological insulators in 2D and 3D with antiferromagnetic order due to similar symmetry arguments. Dirac case I have shown. You can have also these two guys, but these two guys you can equally find in ferromagnets. But these two guys you cannot. So this antiferromagnetic effective symmetries, time reversal effective symmetries which you have there, for instance this combined time reversal and spatial inversion symmetry, is not present never in ferromagnets. So here we have another advantage why to use beside all these other nice things about antiferromagnetic spintronics. And here is a proposal, for instance, for application as topological antiferromagnetic transistor, where by the mechanism which I described, you can, in an ultra-fast way, switch between on and off topological currents. So by this, let me summarize. So in the first part, I have shown that for nice spin-orbit torques, we need to break symmetries. In the cases of this typical ferromagnetic heterostructures, you need either interfacial symmetry breaking or global inversion symmetry breaking by the bulk, like in this gallium manganese arsenic. And in antiferromagnets, you can have a very efficient and very fast guy, which relies on the local non-centrosymmetric antiferromagnets, as I explained it on this PT symmetry. And in the second part, I have shown you that it's really possible that Dirac fermions and spintronic effects can coexist in this type of antiferromagnets, and that it has actually two benefits. First is that you can control that you can control the Dirac fermions by Neél Spinorbit Torques. This is one of the difficulties in topological matter, to control efficiently the Dirac or quasi-particles. And another benefit goes in the opposite, other way around logic, where basically this presence of these Dirac fermions, either in real space or in some other space, in a K-space or in some other combined spaces, they can lead to extremely large topological magnetotransport, as I have shown on this topological anisotropic magnetoresistance. By this, let me thank you to all collaborators and you for your attention. Thank you.